Hello everyone. Welcome to part 7 in our series on solving differential equations using Laplace transforms. So in previous videos in this series, we've seen all the techniques in detail that we need to know in order to use this method. Today I just want to do kind of like a wrap-up problem, right, where I'm going to assume that you've seen those techniques in the other videos, and we're going to use it to solve this problem, not because it's necessarily a super hard problem, just because it kind of brings it all together. Okay. So I've already written down the equation that I want to solve. Here it is, y double prime minus 6y prime plus 9y equals e to the x with these initial conditions. Y is the function of x that we're trying to solve for, and because I'm giving two initial conditions for a second order differential equation, we know that our solution is actually going to be unique. Okay, let's go to it. Okay, the first thing we do in this technique, we apply the Laplace transform to both sides of this equation. So I'm just going to go right ahead and do it. The Laplace transform of the second derivative is s squared times capital Y. Capital Y is the Laplace transform of y of x. Minus s times y of 0 minus y prime of 0. That's the Laplace transform of y double prime. Minus 6 times the Laplace transform of y prime, well, that's just s times capital Y, minus y of 0. And then finally, we have 9 times capital Y, that comes from this term, equals the Laplace transform of e to the x, well, that's just 1 over s minus 1. Okay, there's our transformed equation. All right, so continuing on, I usually like to collect all the terms with capital Y, so that way we can solve for capital Y. I get y times s squared minus 6s plus 9, okay? These other terms, I'm going to move to the other side, and I'm going to substitute for their values. Okay, so I get equals 5/4 s plus 17/4. Scroll down a little bit, that's y prime of 0. Minus 6 times minus y of 0, that's 6y of 0, but I'm moving it to the other side, so I get minus 6y of 0. That's minus 30/4, and I still have plus 1 over s minus 1. Okay. Well, first thing to note, this thing right here is really s minus 3 quantity squared. That's what this thing is. Okay, so I'm going to divide both sides of this equation by s minus 3 quantity squared. Right, that's going to give me y by itself, which is kind of nice. 5/4 s over s minus 3 quantity squared. Plus, now 17/4 minus 30/4, that's minus 13/4, that's not so nice. Okay, so I'm going to just change that plus to a minus, and I get 13/4 over 1 times 1 over s minus 3 quantity squared. Okay, and then I still have the last term here, which is kind of a not very nice fraction, 1 over s minus 1 times s minus 3 quantity squared. Okay, so here's the stage where you kind of need to step back and figure out what it is you're going to do. And just decide if I can get if I know what my approach is going to be. For this term, I'm thinking partial fractions. For this term, I think this is okay. I think I recognize this as the transform of a function. We'll come back to this, but I think I don't have to do anything with this. This one I'm a little worried about. I don't recognize s over quantity s minus 3 squared as the transform of a function that I know. Okay, and this is where this is possibly a tricky thing. With a little bit of experience, you learn to do certain things. So for example, in this case, I'm going to subtract 3 from s on the top and add 3. I can do that for sure because I'm just adding 0. The rest of this stuff, that's just going to stay the same. I'm going to copy it right there. Okay, so I didn't do anything to this. I just added 0, which I can do. Why did I do that? Okay, the idea is that if I can split this up into s minus 3 over the denominator plus 3 over the denominator, then I'm going to be able to see something that I recognize. Let's see what I get. Y equals 5/4. Okay, s minus 3 over s minus 3 quantity squared, well, that's just 1 over s minus 3, plus 3 over s minus 3 squared, and that whole thing is multiplied by 5/4, and I still have this term, which I'm just going to shrink a little bit so I can fit it into here, but I didn't actually do anything with that yet. Why did I do that with the plus 3 minus 3? Well, this term is good. I know what the inverse transform of this is. This term, I can add to this term, and I said before, I think I know what that transform is, right? So really a big part of this is knowing those transforms of the basic functions so that you can look at this and say, oh, wait, if I subtract 3 and add 3 to this, I'm going to get this, which is something I can deal with. Okay, let's simplify this a little bit because I can take this term and add it to this term. Okay, so I'm going to get y equals 5/4 times 1 over s minus 3. Okay, I'm going to get this times this, that's 15/4 minus 13/4. Well, that's just 2/4, which is 1/2 times 1 over s minus 3 squared. And then I still have 1 over s minus 1, s minus 3 squared. Okay, that's looking a lot better. I'm going to copy this down a little bit so that we don't have to write it again. Here we go. I've written the differential equation we're trying to solve up here so that we don't forget what it is we're doing. Sometimes you get bogged down and forget what you actually were trying to solve in the first place. Okay, let's look at this one next. Classic technique to use for Laplace transforms is partial fractions. Okay, so we have to break that fraction up into partial fractions. Partial fractions tells us we need an a over s minus 1 plus a b over s minus 3 squared. Let's just make it b over s minus 3. Plus c over s minus 3 squared. That's what I needed. Okay, let's multiply both sides of this equation by this denominator. That's going to get rid of the fractions. And I get 1 equals a s minus 3 squared because the s minus 1 cancels. Here the s minus 1 doesn't cancel, and I still have 1 of the s minus 3 terms. And here I just have an s minus 1 term. Okay, there's two ways to go here. You can FOIL this all out and then compare the same powers of s. So for example, I'm going to get an as squared plus a bs squared. There's no other s squared terms, and there's no s squared term over here. So that's going to mean that a plus b equals 0. And you can continue on in that way, get a system of equations, and then solve the system of equations. But in this case, I have some nice, easy-to-see factors. So I'm just going to use what's called a variation of the Heaviside cover-up method, where I just plug in values of s. Remember that this equation has to work for every value of s. Okay, so for example, if I plug in s equals 1, then I get 1 equals 1 minus 3 is minus 2. Square that, you get 4. So I get 4a. And then these other two terms disappear because I plugged in 1, and s minus 1 is 0. Well, that's nice. I very quickly get that a is equal to 1/4. Let's plug in a equals, what should I plug in? Yes, that is totally right, 3. Why do we do that? To get rid of everything within s minus 3. This disappears, this disappears, this stays around, and it's actually just equal to 2c. Therefore, c is equal to 1/2. Okay, finally, what's another easy thing to plug in? You can plug in anything. I'm going to pick 0 because that seems really easy. So that gets me 9a plus 3b minus c. Okay, well 9a is equal to 9/4 minus c, that's equal to minus 2/4, and then plus 3b. Sorry, 3b. Okay. Well, let's simplify that a little bit, and I get 1 minus 7/4, which is minus 3/4, equals 3b. So I get b is equal to minus 1/4. Okay, that's not so bad. We got our three constants a, b, c. I'm going to copy this whole messy stuff up here. Let's copy this down here. Okay, there we go. Okay, and I can fill in for a, b, c. Let's get rid of those and just fill in the numbers that we actually got. C was 1/2, that was over here. B was minus 4th, that's here. And A was 1/4, that's right there. Yes, A was 1/4. Okay, that's where we are. All right, let's actually write down what we have for y after all that partial fraction stuff. Okay, first I see 5/4, 1 over s minus 3, minus 1/4 over s minus 3. Okay, well that's just 1 over s minus 3. Okay, so I'm going to cross out the terms so we don't get mixed up and use terms twice and stuff like that. Okay, how about this term? That comes from the first part of this. That looks nice and simple. Let's use that one right away. So that's going to be plus 1/4 times 1 over s minus 1. Okay, get out our nice little orange thing. We got rid of that. What else do we have left? I have 1/2, 1 over s minus 3 squared, plus another 1/2 over s minus 3 squared. This looks like it's simplifying pretty nicely. That's just 1 over quantity s minus 3 squared. Okay, and we got rid of this one, and we got rid of this one, and we got rid of this one now because we used all three terms in our partial fractions. So we actually did it. We finally solved for capital Y, and we got this really pretty straightforward expression. Let me copy it down one more time here. There we go. That's what we got. Okay. It's hard to believe that what we had was really just this, which isn't so bad. Okay. At this point, hopefully you recognize these as the transforms of functions that we know. So I'm going backwards here. What function has a transform of 1 over s minus 3? Well, that's just e to the 3x. What has a transform of 1 over s minus 1? That's just e to the x. Now this next term looks a little tricky. I do know that the transform of 1 over x is 1 over s squared. So this looks almost like that, except instead of s, it's s minus 3. That's just a shift. So we know, therefore, that this is just the function x e to the 3x. There we go. If you want to write it a little more nicely, we could say this is x plus 1 times e to the 3x plus 1/4 times e to the x. That is our solution. Now, you might have known another technique to solve this differential equation up here, right? Using different techniques, maybe, I don't know, undetermined coefficients, another method that's useful for this kind of scenario. Might even be easier, right, than using Laplace transforms to solve this equation with these initial conditions. But this is another way of doing it. And in a later video, you'll see that these Laplace transforms can solve differential equations that we haven't been able to solve using previous techniques. Well, that's it for this video. I hope you enjoyed it, and I'll see you next time.